This is the first of two video lectures on entropy. In the second video, we're going to go over statistics and what entropy really means. And from that, we'll figure out what temperature really means. In this first video, we're going to talk about how to work with entropy, how to calculate changes in entropy, and that sort of thing. The second law of thermodynamics can be stated in three different ways. One way is to say that there are no perfect heat engines. As we studied the Carnot cycle, we found that if you beat the Carnot efficiency, effectively heat can flow from low to high temperatures without any work being put in. And that's just silly. So that can't happen. We also noted that the Carnot efficiency goes to 100% when the cold reservoir goes to 0. So saying that there are no perfect heat engines is equivalent to saying that you can't get to absolute 0. If you could make the Carnot efficiency equal to 1. Now, why can't you get to absolute 0? Well, because the entropy of a closed system can't decrease. In fact, it can't even remain constant unless all of the processes that happen are reversible. How does that imply that you can't get to absolute 0? We'll find that out in part 2. But for now, let's focus on what is entropy good for. Well, one thing you can do with it is you can quickly debunk ideas, or you can find theoretical limits. It's kind of like when we studied the Carnot cycle. You don't actually make a Carnot engine, but by coming up with this theoretical engine and understanding it, it told us about the limits of what you can do with real images. And entropy's a similar type of thing, where if somebody comes along and shows you, a perpetual motion machine, you can say, second law of thermodynamics, you're crazy, this doesn't work, you made a mistake. When you take a more advanced thermodynamics class, which you may be surprised to hear most of you probably will, you'll learn other things you can do with entropy, and it can help you calculate a lot of different things. But one of the exciting things about studying entropy is it will explain what temperature really is. We will finally know what temperature means, what it means for something to be at twice the temperature as something else. But what exactly is entropy? You've probably heard that entropy is a measure of disorder. But yeah, that's not a very precise definition. What is disorder? When we do thermodynamics, we will come up with a very precise definition of what we mean when we say entropy. And hopefully when we do that in the part 2 video, you will see that it is somehow related to disorder. All right, so for now, we'll just move ahead with how to do calculations with entropy, and we'll define it more precisely in the second lecture. But know that entropy is about probability. It is very improbable that we will ever observe the entropy of a closed system decrease. So the second law of thermodynamics is a probabilistic law. But in the limit, as the number of particles goes to infinity, probability becomes fact. And in the limit, as you get a number of particles comparable to what you find in everyday stuff, you find that the second law of thermodynamics is effectively, for all practical purposes, true and undeniable. Consider the air in the room that you are in. Now imagine in your mind, just divide the room in half in your mind. Now if there were only 2 or 3 particles in the air, 2 or 3 molecules of air in that room, sometimes you would find, one particle on one side and the other particle or 2 on the other. But there would also be times when you would find all of 2 or 3 particles on one side of the room. Now, going from having some particles on both sides to all of the particles on one side, that is going from a high entropy to a low entropy. So the entropy of the room goes down. But with just a few particles, you don't have a thermodynamic system. The second law doesn't really apply. But if you have atmospheric pressure in your room, you have lots and lots of particles, the probability of all the particles just happen to randomly wander to one side of the room, leaving a perfect vacuum on the other side, it's just, the probability of that happening is just infinitesimally small. It's not even worth considering. And so in the thermodynamic limit, where you have a lot of particles, the second law of thermodynamics, for all practical purposes, is absolutely true. Now, to understand entropy, we have to know the difference between a reversible and an irreversible process. A reversible process is something where if you videoed what you did and then played it backwards, the laws of the universe would be happy with the video going backwards. Whereas an irreversible process is one where when you play the video backwards, alarms go off and the laws of physics are offended. So for example, a free expansion. Imagine you had a divider dividing your room in half and keeping all of the air on one side of the room. And then you slid that divider out and the gas filled the entire room. If you videoed that and played it backwards, what you would see is a bunch of gas spread throughout the room, and it just like whoop, goes to one side on its own as you insert the divider. There's all kinds of wrong with that. That doesn't happen. So a free expansion is an irreversible process. You play the video backwards, and it's just wrong. Heat conduction from cold to hot is another example of, heat conduction from cold to hot doesn't happen. Heat goes from hot to cold, right? So imagine I have a pot of boiling water and a pot of ice water, and I bend a copper rod and put one end in each of the pots of water. Heat will conduct from the water at the higher temperature down to the water at the lower temperature. Now, if you videotape that and play it backwards, now you have a video of heat going from something cold to something hot. And heat does not conduct from cold to hot, it conducts from hot to cold. So there's something wrong with that video when you play it backwards. So heat conduction is not a reversible process. Scrambling eggs is another irreversible process. You scramble the eggs, you play the video backwards, and it's hilarious. Reversible processes are things like an adiabatic expansion. So if I drop a basketball and it bounces on the floor, that's not truly a reversible process. It's just not truly an adiabatic process, but it's an approximation. So imagine that was a perfectly adiabatic process. The ball goes down, it compresses, the pressure goes up, the temperature of the gas goes up, but then it expands again and the ball pops back up. So that's reversible. An adiabatic process is reversible. You play that backwards and you see the ball bouncing and everything's fine. A constant temperature expansion is reversible. So imagine I have a piston and it's sitting in ice water and I'm holding the piston down and I let the piston move up and the gas underneath it expands. But as I do that, heat flows in from the ice water, keeping the gas in the piston at 0 degrees C. If I play the video backwards, now I'm pushing the piston down and heat's flowing out of the air into the water, but that's okay because they're both at 0 degrees C. So the video forward, the heat flows from the water to the gas. In reverse, the heat flows from the gas to the water, but that's fine because they're both at the same temperature and the video is fine backwards or forwards. Now, if I did a constant temperature expansion, but it wasn't in ice water, imagine, if you will, I have a little temperature sensor and some heaters, and as the gas expands, the temperature sensor is going to notice that the temperature is trying to change, and it's going to turn on the heaters and keep the gas at a constant temperature. That's not reversible. If you play that backwards, you're like, wait a minute, now the heaters are sucking heat out of the gas, right? That's not reversible. But for the gas, it is, right? Because the gas doesn't know whether the heat's coming from heaters or from ice water. So for a constant temperature expansion or compression, it is reversible for the gas. Whether or not it's reversible for the environment around the gas is another question. Now, ice melting is reversible, sort of. Imagine you had a beautiful ice sculpture and it melted. You play the video of that backwards, and now you have a puddle of water turning into a beautiful ice sculpture, and that's just wrong. Okay? So that aspect is not reversible. But if we just think about the molecular process of ice melting, that is reversible. So imagine, if you will, that I took a cup of water and I put it in a freezer. The water freezes. Now I play that video backwards and I see ice melting. That's perfectly fine as long as the freezer is at 0 degrees C, right? Because heat can flow from water to the freezer or from the freezer to the water just fine as long as both of them are at 0 degrees C. But if my water is at 10 degrees C and the freezer's at minus 15 degrees C, I put it in there, and as the water cools down, that's heat conduction, that's not reversible, right? Then my water's at 0 degrees C, and heat flows out and it becomes ice. But once again, the heat is flowing from water at 0 degrees to the inside of my freezer, which is at minus 15 degrees C. That's not reversible. I play the video backwards, and it's wrong. Heat's flowing from low temperature to high. But if my freezer were at 0 degrees C, it would be reversible. So ice melting or water freezing is reversible for the ice. It may not be reversible for the system around it, for the environment around it. So ice melting on my countertop, that's not reversible, right? Because heat's flowing from the room into the ice, and the room is at higher temperature. You play that backwards, and you have heat flowing out of the water into the room, and heat's flowing backwards. But we could have melted the ice in a 0 degree environment, and that would be reversible. So it's reversible for the ice, but maybe not reversible for the environment. An irreversible process, once again, is something that won't happen backwards in nature. If you played the film backwards, physics would cry. But a reversible process is one where you play the film backwards and physics doesn't mind. Now, we talked about how ice melting is reversible for the ice, but maybe not for the environment. So we need to talk about isolated or closed systems versus open systems. In an open system, for example, my cup of water, when I put it in the freezer, my cup of water is an open system because it can exchange heat with things around it. Heat flows in and out of my system. That is an open system. In an open system, the entropy can change. The entropy can actually go down. All right, so if I have my glass of water and I put it in the freezer, as the water freezes, its entropy is going down. And that's okay because it's not an isolated system. Heat is flowing out of my water into the icebox, into the freezer. So the entropy of my water goes down, but the entropy of the freezer goes up. And I can still obey the second law of thermodynamics because the second law says the entropy of an isolated system, a closed system, cannot decrease. My water's entropy is decreasing as it turns into ice, but it's not a closed system. Now, if we imagine that my freezer has perfect insulation, no heat flows in or out of it, my freezer is a closed system. So I put my water into my freezer and I close the door. Now my freezer is an isolated system. It's a closed system. So the entropy of that system cannot go down. So if the entropy of the water goes down, that means the entropy of the rest of the freezer must go up, at least as much as the water goes down, because it's an isolated system and the entropy can't go down. Now, if the water freezes in a reversible way, if the freezer is at exactly 0 degrees C, that means that the process for the whole freezer was reversible. If a process is reversible, I can do it backwards. So that means the entropy can't change, because if the entropy went up one way, it would have to go down the other way, and the entropy of an isolated system can't go down. So if the water freezes reversibly, if the freezer is at 0 degrees C, that means when the water freezes, the entropy of the system doesn't change. But if it happens irreversibly, if my freezer's at negative 15 degrees C and I put my water in at 0 degrees C, my water, as it freezes, its entropy will go down, but the freezer's entropy will go up by more than the amount that the water went down, because we had an irreversible process, and an irreversible process will increase the entropy of an isolated system. The entropy of the universe always goes up with an irreversible process, and the entropy of the universe stays the same for a reversible process. So an increase in entropy equals an increase in disorder, whatever that means. How can we actually calculate how much the entropy changed in a system? Well, the equation we use is this. A little infinitesimal change in entropy is equal to a little infinitesimal amount of heat flowing in divided by the temperature of the system as the heat came in. Now, the little subscript r means that this equation is only valid for reversible processes. Now, if I want to find a macroscopic change in entropy, I just integrate this, and I find that the change in entropy as some heat flows into a system is just the integral of dqr over the temperature. And I just do that integral, and I find the change in entropy. Now, there's three questions I want to ask. First of all, where did this equation come from? Well, we'll get there. We're going to find that out later. We're going to find that out in part 2, right about the time we figure out what temperature really is. So we'll get there. Another question is, why do you get a bigger entropy change when heat flows in at a low temperature and a smaller one when the same amount of heat flows in at a higher temperature, right? ds is dq over t. Why is that 1 over t in our equation? What is the physics behind that? What's the reasoning behind that? Well, we'll get there, right about the time we figure out what temperature really is. All right? Our third question is, how do we calculate the change in entropy if the process is not reversible? This question we're going to answer right now. What you do is you just find a set of reversible things you could do to get you from the initial and the final state. Unlike the work done, which depends on, the process you go through, it depends on the plot on your PV diagram, entropy does not remember how you got there. Entropy is an equation of state. So to find the change in entropy when you go from state A to state B, all you have to do is find some set of reversible processes that get you from state A to state B and use that to calculate the change in entropy, even if that wasn't what you really did. Okay? So here are some examples. Remember, the change in entropy is just the integral of dq over t as we go from no heat to all of the heat having entered the system. Let's consider ice melting. Now, ice melting is not necessarily reversible, right? If we have ice melting on our countertop in a room at 25 degrees C, that's not reversible. But the ice doesn't care, right? All we need to do is find a way to get the ice from its initial to its final state reversibly, and we can use that to calculate the entropy. So what we do is we say, okay, it's melting on the counter, but the change in entropy for the ice would be the same if it melted in a 0-degree icebox, which is reversible. And then we say, okay, great, now I've got my reversible way, I can do my integral. All right, so I say, well, delta S is 1 over T. The temperature's constant for ice melting, so it comes out of the integral, and then we just have the integral of dq, and the integral of dq is just q, right? It's just the total heat that came in, but the heat that comes in is just the mass of the ice times the latent heat of fusion, so the change in entropy is just ml over 273.15 Kelvin. Now remember, that's not a temperature difference, that's an absolute temperature in our entropy equation, so that the temperature must be in Kelvin to get the right answer. How about an isothermal process? Imagine I have a gas inside of a cylinder with a piston holding it down, and as the gas expands, the piston's sitting in ice water and heat flows in to keep the ice at a constant, or the gas at a constant temperature. That might not really be what's happening, right? We might have an irreversible isothermal thing going on, but as far as the gas is concerned, it's reversible. Right? We can think of a reversible way to do this. And when we do that, we say, oh, well, once again, for an isothermal process, the temperature is constant. It comes out of the integral. And we just get 1 over T times the integral of dq. And the integral of dq is just Q, just the total heat that came in. So the change in entropy is just Q over T. But for an isothermal process, there is no change in internal energy. And since the change in internal energy is the heat that flows in minus the work that comes out, that means Q is equal to work, and we can rewrite the change in entropy as just the work done in the isothermal process divided by the temperature. Well, maybe we don't know Q, or we don't know work. Maybe we know the change in volume of the gas as the isothermal process happens. Well, we could calculate Q or work, or we could just go back to the integral and say, well, wait a minute, it's the integral of dq over T, but dq is just d work, and work is pressure d volume, all right? But we don't know how the pressure changes. We know how the volume changes. And so we use the ideal gas law, and we'll replace P with nRT over V, and the T's cancel out, and we're just left with the integral of nR dV over V. And now, instead of our limits being going from 0 heat to Q, all of the heat having gone into the system, we say, well, what's the volume when no heat has gone into the system? Oh, that's volume initial. So we replace the 0 with V initial, right? That's the corresponding endpoint when we go from heat to volume. And when we've put all of the heat in, that's when we're at the final volume. So that integration limit becomes V final. And N and R are constants. They come out. The integral of 1 over V is just the natural log. And we find that the change in entropy for an isothermal process can also be written as NR times the natural log of V final over V initial. How about an adiabatic process? Well, for an adiabatic process, we get the integral of dq over t, but we don't integrate anywhere. We don't put any heat in for an adiabatic process, so the change in entropy for an adiabatic process is 0. Simple enough. How about an isochoric or isovolumetric process? Well, is it reversible? Well, we just imagine a reversible way to do our isovolumetric process, and then we say, well, dq is just ncv dt, right? A little bit of heat, Q is equal to ncv delta T, so a little bit of heat, dq, is just ncv times a little bit of temperature change, dt. Put that into the integral, n times cv, those are constants, they come out of the integral, we get ncv times the natural log of T final over T initial. Isobaric process, very similar. Q is equal to ncp delta T, so a little bit of Q, dq, is equal to ncp dt, right? We plug that in for dq in our integral. The ncp comes out. We just have dt over T. That's just the natural log, and we get ncp, natural log of T final over T initial for our isobaric process. How about thermal conduction? Thermal conduction is not reversible, so we have to come up with a reversible way to get from our initial to our final state, all right? And so what we do, let's just consider, so let's imagine I have two blocks. They're at two different temperatures. I put them together and they come to thermal equilibrium. How much does the entropy of one of those blocks change because of thermal conduction? Well, we just have to find a reversible way to get that block from its initial temperature to its final temperature. Well, what we could do is we could take the block and put it in contact with a thermal reservoir, a large thing at the same temperature as the block. And then we let an infinitesimal amount of heat flow between them. Then the temperature changes infinitesimally. All right, infinitesimal changes are reversible. So we're good. Now we take the block away from that thermal reservoir. Its temperature has changed infinitesimally. We're going to put it in contact with another thermal reservoir at its new temperature, which is infinitesimally different from its original temperature. And we're going to let a little more heat flow. And we're going to do that over and over again. We're going to do an infinite number of infinitesimal changes in order to get that block to its final temperature. Well, with each step, the amount of heat that goes in or out of the block is just mc times delta T, dt, the little temperature change. So we can plug that into our integral for dq, and once again, the m and the c, the mass and the specific heat come out of the integral, they're constants, and we just get the integral of 1 over t, which is the natural log. How about a free expansion? So I have all of the air in the room on one side of a partition. And then I pull the partition out and the air goes and fills the whole room. That is irreversible. How do I find the change in entropy? Well, I just say, well, what are the initial and final conditions? Initially, I've got a gas at some temperature, at some pressure, confined to some volume. Then the partition disappears. So imagine I have a gas molecule. It's about to hit the partition, and then suddenly the partition's not there, so it just keeps going. Its velocity doesn't change. Its kinetic energy doesn't change. So in a free expansion, the kinetic energy of the molecules don't change, which means the temperature doesn't change. So I go from some initial volume and temperature to a final volume, but at the same temperature. How could I have done that reversibly? I could have done an isothermal reversible expansion. So for a free expansion, I'm going to get the same entropy change I would have gotten with an isothermal process, which we already calculated. So that's how we find the entropy change. Now, it turns out when I have ideal gases, I can come up with an equation that I can just blindly use for any process. I just need to come up with a generic equation that can get me from point A to point B. So imagine I start with my gas at the left point, at high pressure, low volume, and it goes to some other point, point B, say the point on the right. And let's say it does some weird process shown with the yellow line, and maybe it's reversible, maybe it's not. All right? Or maybe I do some process like a free expansion where I can't even draw a line from point A to point B because the gas doesn't have a well-defined volume as it's expanding. Right? It doesn't matter. If I want to know the change in entropy when I go from point A to point B, all I have to do is come up with any set of reversible processes that will get me there. So let's do this. Let's first do an isothermal process that gets us to the final volume. As we do that, the entropy changes by NR natural log V final over V initial, right? We already calculated that. That is what we found for the change in entropy for an isothermal process. Well, now we're at the correct volume, but we're not at the correct pressure. So let's do an isobaric process. And we already calculated what you get for an isobaric process. It's just NCV times the natural log of T final over T initial. So here's a generic equation. Any 2 points on a PV diagram can be connected by an isothermal and an isovolumetric process. And that's the entropy change that you get from each of them. So, write this equation down in your notebook, and now you've got an equation. Doesn't matter what happens if you have an ideal gas and it goes from one temperature and volume to another temperature and volume, this equation will tell you the change in entropy. Now, when can entropy decrease? The second law of thermodynamics says that the entropy of a thermodynamic system that is isolated cannot decrease. So when can entropy decrease? It can decrease when the system is not isolated. So, for example, our glass of water at 0 degrees C inside of a freezer. As heat flows out of the ice water, of the waters, and it turns into ice, remember our integral dq over t, if heat is flowing out, we're integrating backwards, right? We're taking heat out, and the entropy of our water will actually go down as it turns into ice. But that's okay, because it's not an isolated system. Heat is flowing out of it. But if we imagine our freezer is thermally insulated really well, so it's a good approximation of an isolated system, no heat flowing in or out of our freezer, the entropy of the freezer cannot decrease because it's an isolated system. So if the entropy of the water goes down, then the rest of the freezer's entropy must go up. Now, if the freezer's at 0 degrees C and our water is freezing reversibly, then the entropy of the freezer will go up by exactly the amount that the water goes down, such that the whole isolated system has no change in entropy. For a reversible process, our isolated system has no change in entropy. But if the freezer's at negative 15 degrees C, then as the water freezes, heat's flowing from something at a higher temperature to a lower temperature. That's not reversible. That means that the change in entropy of the ice, we can calculate that, right? We have our formula. When we calculate that, the entropy of the freezer must go up by more than the amount that the water goes down. Because when an irreversible process happens, the entropy of an isolated system goes up. So the entropy can decrease if the system is not isolated. The entropy will stay the same when you do a reversible process for the whole system. And when you do an irreversible process, the isolated system's entropy will increase. So you can only have a decrease for an open system, a system where heat's flowing out of it. Whenever you do a reversible process, the entropy of the universe doesn't change. When you do an irreversible process, the entropy of the universe goes up. So the second law of thermodynamics, again, says that the entropy of a closed system can't decrease. And we'll find out why in part 2. But because the entropy can't decrease, that means you can't get to absolute zero, which means there are no perfect heat engines. Now, eventually, the entropy of the universe will just keep going up, and eventually we get to something which is known as universal heat death, the heat death of the universe. The whole universe will be at a constant temperature, maximum disorder, and you'll no longer be able to turn heat into work because you'll have no cold reservoir to exhaust heat into. And in the words of T.S. Eliot, this is the way the world ends, not with a bang, but a whimper. But we don't have to worry about that because the heat death of the universe is a long ways away. That's the end of part 2. We'll see you back in a minute. Sorry, that's the end of part 1. We'll see you back in a minute for part 2.